finish it earlier. So yeah, that's pretty much about the paper there. So because I don't think I could explain very clearly with this in online classes. So I want everybody to learn about this semiconductor device, and this is very important, right? Basically, when you have this P and N junctions, when you bring them together, right? That's what you are making the real devices. So what happens is, like in P, we know basically you have holes, dominant carrier, right? So when you have holes, what do you get here? Typically, the acceptors, right? So acceptors become negatively charged, right? Remember what we had was, so if you had some acceptor atoms, so they get electrons from this one. That's why we had holes here, right? So when you have holes, what do you get here? You get negatively charged acceptor ions, right? If you take like a boron, so boron becomes negatively charged. In the process, you have holes here. If you have holes as your carrier, then the immobile ions are negative, right? So they don't move. So only these holes they are the majority carriers. So you have to be careful, these two terms, majority carrier versus minority carriers. Like if you are talking about like solar cells, mostly you are talking about how the minority carriers are moving. So if in the N-type, what happens? N-types, you have donor atoms, right? You are giving electrons to the conduction band. So if you do this one, that means you have these are your majority carriers. They are the ones they can move, right? In the process, what do you get here? If you give electron here, this becomes positively charged donors. So like phosphorus. Phosphorus gives one electron to the conduction band, then phosphorus becomes positively charged, right? So that means what you have here is positive, they are Nd plus. So they don't move, right? So they are immobile. So only electrons, they are moving, here holes are moving. So that's why when you bring together, what happens? These electrons will move to this side, holes will move to this side, then they recombine, right? So then you lose electrons and holes, but they are still there, right? So nothing happens here. Here also these plus ones, they are already there, but you are depleting your holes from this side and electrons from this side. That's why we have this. Now we have negative charges here, positive charges here, then you have electric field in this direction. We call this is the depletion region. Depletion means what? Depleted of majority carriers, right? That's important thing. So then when this happens, you have electric field, right? When you have electric field, what happens? You have a potential gradient, right? Electric field means basically potential gradient. That means the flat bands, they have to bend it, right? To have that electric field. So then how does that happen? This is another thing a lot of people really don't understand, how these bands are going to bend. So in the class we talked about this side, we had the p-type, right? P-type means your Fermi energy sphere. Intrinsic means Fermi energy is at the center, right? So metals, we have to be careful. Metals means you have energy state up to your Fermi energy. Everything below is filled, everything above is empty, but they are unoccupied, right? But in semiconductors, if it is intrinsic, your Fermi energy is right at the center. If it is p-type, that means you make your Fermi energy move towards the valence band, right? That means your Fermi energy is somewhere here. So if you have n-type, so typically intrinsic here, now n-type means you are having more electrons, that means your Fermi energy is going to move towards the conduction band edge, right? So now if you bring these two together, this is one system, you cannot have two different Fermi energies. You should have one equilibrium Fermi energy. In order to have this one same, this has to kind of offset, so that this you will have the same Fermi energy. Now you have one here, you have one here. When you have these two together, so they will have to bend so that you have same Fermi energy, right? How does it bend? That is the key. So you have to really understand this one, not people don't not really. So here, most of your electrons are here, right? So these are at high energy. So that means these electrons will be transferred to low energy. That means you are losing electrons from here. That means this becomes positive, right? So this side becomes negative. That means your electric field is this direction. So that means if you say this is positive, this is negative E. Negative means your slope should be negative. That means more than 180, right? That's the slope is negative. Slope positive means it's less than 90 degrees, right? So that now your slope should be negative, so that it should bend like this. So this is how they are going to bend, right? So they are bent like this, so that now your Fermi energy, this becomes one common Fermi energy. That is your equilibrium Fermi energy. You can see now your bending is this way. Typically you have flat bands. Now because of the electric field that is in this direction, you have these bands are bent, because we know E is given by dV by dx, right? Negative. That's how we have speech. So now imagine if I had this way, how does it? I think this is very important. So if I had N-type here and P-type here, that means here your Fermi energy is here, right? N-type. Here Fermi energy is here. Now these electrons are at high energy. That means that electron will go from high to low. That means this becomes positively charged, this is negative. That means your electric field is positive direction. That means it's a positive, right? That means your slope should be, here your slope is negative. Now your slope should be positive. That means it should bend this way, right? So now you should have something like this. Sorry, that is, that is positive, right? Yeah. Then your common Fermi energies. This is how. Exactly. You have to argue how it's going to bend. So here it is bending this way. So just let me ask you a simple question. If I have a metal and semiconductor, anybody knows what happens? Most of the time when you make a device, you have a semiconductor, you have to use a metal like gold, platinum or something, right? That means you have a metal and semiconductor junction. Then what happens? Suppose if I have metal here, your Fermi energy is here, right? Because up to here, all the states are filled. Now, I connect it with the semiconductor. Suppose this semiconductor is N-type. Now what happens? Your Fermi energy is here, right? So this is higher. So then this should give electron to this one, right? But remember, metals, so if you put electrons, do you think the EF will change? Metals have so much electrons, right? So if you put few electrons, your Fermi energy is not going to change. So that will be constant. So now, so this will become positively charged, right? So that means you have electric field in this direction. That means this one should bend so that your slope should be negative. Slope negative means what? Something like this. This is what happens if you have a metal versus N-type semiconductor. You have some barrier. Anybody knows the name of this one? Metals, if you put with the semiconductor, you have something called a Schottky barrier. Maybe you have heard about this. Schottky So that's why we have to be very careful what kind of metal you have to use when you make this device. If the barrier is too high, it's not good, right? Electron cannot go from here to here because you have a large barrier, right? That's why you have to pick the right metal, whether it's aluminum or gold or platinum, depending on your semiconductor properties. Because we know each metal has something called the work function. Work function is your energy from this vacuum level to your Fermi energy, right? That determines this Schottky barrier. Okay, can you tell me if I have a p-type material with metal? This is your metal, this is your Fermi energy, right? Now I bring material with p-type material. That means your Fermi energy is here. So now what happens? Electron will go from here to here, right? So that means this becomes negative charge. So that means you have electric field, this is positive electric field, right? So now this is because that Fermi energy doesn't change. Metals, if you take few electrons here and there, it doesn't change the Fermi energy, right? So now how is it going to bend? You need to have positive slope, right? So that means actually this is going to bend something like this. This is your, that is the way how this metal versus p-type semiconductor, how the, so you can see there's a barrier for actually holes here. This is a barrier for holes. Here this has a barrier for electrons. Is that clear? So everybody has to really understand how, if you bring two semiconductors, so semiconductor and metal, how the bends are going to the, your bands are going to be bent. So usually people don't discuss these things in detail, so that's why I think everybody should have a clear idea about this.
That's called a Schottky?
Schottky barrier, yes, yeah. Because if you have any metal versus semiconductor, always you have a Schottky barrier. You need to make sure that Schottky barrier is as small as possible. Otherwise, it's very difficult for electrons to go from semiconductor to metal, right? If you have any device, what you need eventually, you need to get the electrons to your circuit, right, to the metal. If you have a very bad high Schottky barrier, that's bad for the device. Okay, so last time we talked about all these things, right? I think you have to really understand what I was talking about. P-type, you have holes, these are the acceptors, right? They are immobile. Here, electrons, N-type, these are the acceptors. So now when you bring these two together, we talk about how things are changing. So this is a very nice diagram you can see here. So here you can see you have this hole concentration, you have large hole concentration up to here, right? So how about also the Na minus, right? Accept also, sorry, in accept also you have this N minus value here. So there are no donors here, right? Donors are pretty much 0 here. So that means if you take the, Na minus, yeah. So here P plus, yeah, I think I missed up. Here holes, you have a lot of holes, that's fine, right? No donor atoms, that's 0. Okay, donor atoms are only here, right? So then electrons, no electrons here, right? It's only hole, that's also 0. All what you have is Na minus, right? That's a negative value here. But if you take the total charge, this one plus this negative, that becomes 0. Because all the holes are coming from these acceptors. Because we assume your N, in this case P, right? P is coming mostly from the Na minus. Also we assume all the holes are coming mostly from the donors. So in intrinsic case we know all the holes coming from the same number of holes and electrons should be same, right? Because they only coming from these things. But if you have acceptor levels or donor levels, you get extra electrons from here. So we assume what you are getting here is much higher than what you had in the intrinsic situation. Same thing here. If you get these acceptors here, then most of these holes are coming from this by accepting electrons by this one. So basically we are assuming N mostly coming from the donors, P mostly coming from acceptors. So you can understand here also, right? If it is N type, no holes, 0. Donors mostly, donor value. Electrons, there are no electrons. Oh yeah, that's all the electrons right here. But negative charge, right? So then no acceptors. If you get the total charge, it is flow, right? So now if you want to, if you bring together, we already talked about what happens, right? So this is before. So then also another important thing is, if you have P-type material, mostly you have this Na minus, then you have all the holes, right? These are the, we call the majority carriers, right? So these are acceptors, they are immobile. So if you have this one, what happens typically if you connect with another semiconductor or something? Basically, if you have a large concentration of holes, they will diffuse. There are two things you need to know about. If I have electric field, suppose if I have electric field this direction, these holes will move in that direction, right? That's called drifting. Also, if you have a larger concentration of holes, so these are all confined here. If you let it, if you relax this one, what will happen? They will diffuse, right, from higher concentration to lower concentration. So typically, this diffusion current is given by this charge time, something called the diffusion coefficient, times the concentration. If you have holes, that's basically all gradient. This means what? dP by dx, right? So typically, this is the diffusion current. So if you have an N-type material, that means you have all electrons, right? So then we have equal number of acceptors, right? Nd plus. Nd plus, Nd plus. These are immobile ones. So if you are confined in this one, and if you relax this one, what will happen? Electrons will also diffuse, right? So then that diffusion current from electrons also given by minus qd is that n. It's dn by dx, right? So that's basically the diffusion. This is diffusion current for holes and electrons. This is important. I think you learn all this, right, in the statistical method. So then, like I discussed, band bending. When you do this one, remember, initially it goes here, right? Intrinsic. Now, so you have this new equilibrium Fermi energy. So then we can easily calculate this, how much it is moved. So same thing, this one initially it was intrinsic value, now this is the new equilibrium one, that is the difference. So we can easily calculate this value and this value. The sum of these two will be your total, that we call that's the built-in potential. The built-in potential is basically this one plus this one, because that is the one from equilibrium, how much more and how much less. You have to calculate the EF minus EI, EF minus EV, and basically add the two. That will give you the total, this built-in potential. So we can easily, actually we already did in the previous class. So this is also an important thing, you can understand how everything works. So you have, so if you take this is the depletion region, right? Remember, holes, these electrons move to this side, holes move to this side, they are 3 combined, right? So that means you are depleted of holes here, depleted of electrons here, right? So previously what is the total charge here? 0. Here total charge was 0. Now you lose these positive holes and negative holes. So that means this part is negatively charged, this part is positively charged. That's why you have the electric field in that direction, right? So that's what this is. You have total here, total this one, because from here to here total charge is 0. From here to here total charge is 0. But in this part you have Na minus, right? In this part you have Nd plus. Everything here is all 0. If you have a charge, then you can calculate your electric field. So let me ask, how do you calculate this electric field? ENM. So how do you do that? It's very straightforward. Everybody familiar with the Poisson equation? D squared V over dx squared equals minus rho over epsilon 0 if you have epsilon r. That's it. You can easily solve this one. This one you can write as dv over dx equals minus rho over epsilon 0. What is dv over dx? That's e, that minus e. That means d over dx e equals minus rho over epsilon 0. Now you can solve for e. How do you do that one? If you take this region, suppose this is your depletion region, I'll say this is 0. Suppose this is a p-type, right? This is n-type. So this we call x minus xp. It's a negative side, right? Here we call this plus xn. So what happens in this region? Electric field is 0, right? Total charge is 0. How about here? Electric field is, because in this field your total charge is 0. Right? Only here you have charges. That's why you have electric field. So then you can easily calculate your E by integrating this one. Is that clear? Pretty simple. How do you integrate this one? E equals, this becomes, actually no, this becomes positive, right? Because I have, this is also negative, right? So that means I have E equals rho over epsilon. But rho is what now? If I take this side here, your rho is basically negative Na, right? So I can say Q times Na, that's negative, right? That's your rho divided by epsilon 0 times x. I integrate this one, right? Plus some constant. Now I can find this constant because at x equals minus xp, what is E? Is 0, right? In this region, E is 0. And that means if I plug in this one, at x equals minus xp, your E is 0, then what happens? So your C is what? Bring this one, this becomes 0, then C becomes Q Na over epsilon 0 times xp, right? If you know that depletion region, that means I can write my E as Q Na over epsilon 0, you have x here, plus xp. You can calculate. Same thing you can do for the right hand side. How do you do that one? This one equals, then this becomes, actually this was positive. Yeah, because I calculate in the positive side. Anyway, if you can easily calculate this one, right? So, like this. In the right hand side, this becomes, this is n d, right? And d, that is positive. So then again you can do the same calculation when x equals 0. X equals xn. Your E becomes 0. So then from that you can calculate this your E becomes something Q N D over epsilon 0 x minus x n. You can easily calculate that. Right? So then also we know since this part your total charge is 0, if you calculate at this region, your total charge density also should be 0. So the total charge density would be, suppose this has area, say A times, then the area would be, volume would be A times XP, right? Times your charge, that would be N, in this case NA. This should be equal to A times Xn times Nd. You can see A cancel. You can easily show Xp times Na equals Xn times Nd. So then you can show this E also, this relationship. So what you need is something called this depletion V. What is depletion D? Depth. Oh, D. So this depletion V is basically this one. This is Xn, this is Xp. W means Xp plus Xn. So that you can easily show, right? We know here Xp, Xn. So that means you can easily calculate this W in terms of Xp and Xn. What is W? Xp plus Xn, right? So if you want, you can write as Xp plus Xn means Nd divided by Na times Xp. So that means Xp times Na plus Nd divided by Na. You can calculate all these things. So here I have calculated all these things. So you can check these things. Here, please follow through this one. Is this clear? That's this one, right? Na times Xp. Then also that's equal to that. Doing this way, you can find Xp as W divided by this one, right? So Xp is this one, you can write in terms Wd. Is that clear? So then also, like I said, you can show this one in terms of this one. You can calculate your electric field and all these things. So that's basically that Poisson thing. Okay, so I'm going to give homework problem to derive this one. Very simple. It's just simply use the boundary condition and do this one. Yeah.
So what's the doping? Is that where you'll put it in the region? Or?
Yeah. So this basically Xn and Xp here. So here it is drawn as Nd minus Nd. It doesn't matter. Typically Nd is, if you do Nd, this P type, N type, in the P type side you have negative Na, right? P type side you have plus Nd plus, right?
Yeah.
So, but if you draw as Nd minus Na, that's so electric field, you can see it has that X dependence, right? If you draw E, that's how, because it has linear X value, right? That's how. Then you can find what is the maximum electric field. What is the maximum electric field? When X equals 0. So when X equals 0, you can find the maximum electric field as Em here. So then how do we calculate VBI, the built-in potential? That's the only thing we don't know, right? How do we calculate the built-in potential? Remember how much it changed from original intrinsic value to this one and intrinsic value to this one by this bending, right? If you add these two, you get the built-in potential. See, this one. So this is clear for everybody? How the depletion width is. So if you want to calculate the, I'll get to this one next. Yeah, here. This is how we calculated the, how much. So I think I showed the previous lecture, your N can be expressed as this one. Assuming all the electrons are coming from the donors and all the holes are coming from acceptors. So if you have this one, you can write this one. If you, what is this one? I can write as, just simply take the logarithmic of both sides. So, if you take the N over Ni, Ni is the intrinsic value. Remember always N times P equals Ni squared. This is always true. So N over Ni equals exponential En, that is the Fermi energy, Ef minus Ei, intrinsic value, times beta, right? So then if you take the logarithmic of both sides, log N over Ni equals this beta times Ef minus Ei, right? So if you divide by 1 over beta, like this. Same thing from the other equation, you can say 1 over beta log n P over Ni equals Ei minus Ep, right? Minus this Ef. So that's what from the middle one, this much increase, this much decrease, right? Now you have to add the two. That will give you the total. That's the built-in potential. If you add these two, Ef cancel, you get this. Sorry, you have to subtract. Right? They are in the opposite direction. Then they cancel. Yeah. So then you have Ei is given by basically. So log n of, you have to multiply these two, right? So then you get this NP over Ni squared. You can, so actually I have to, depending on whether you take that positive or negative sign. Yeah. Yeah. So these two now. Yeah, so you have to basically, if you write this way, yeah, so just if you subtract the two, no, add these two, right? So, yeah, one side is moving up, other side is moving down, that means you have to subtract the two, right? You take this. So then you get these two terms coming, Na times Nd divided by Ni squared. That's what the relationship. Yeah. Yeah. This same, this kBt as the beta value, right? Or no beta. Then we have to multiply these two, right? Nd over Ni squared. That's the built-in potential. So whenever you have these two NP junctions, you can calculate how much built-in potential. So that depends on what? Na, Nd, mostly, right? If you have much higher doping, the built-in potential is going to be much higher, right? So not much with Ni squared. So it's mostly, if you can put more acceptors and more donors, your built-in potential can be higher. So you can tune how much built-in potential you need.
Is erbium really popular?
Erbium?
Yeah.
Erbium is not for semiconductors. They are more popular for optoelectronics. Yeah. So typically, we are talking about in semiconductor, the silicon semiconductor, mostly we have something called N++ doping and N minus doping and P++ doping. That can be boron or some other material. So that means this is highly doped. That means you are moving your Fermi energy even into the conduction band, then that becomes N minus minus, or even into the valence band, that becomes P plus plus. That way it behaves more like a metal. So that's why if you make devices, you find this the very highly degenerative doped semiconductors. So is that clear? So when you bring these two semiconductors together, due to band bending, you have built-in potential. So now you can change this built-in potential by applying external bias. That's what we call the forward bias and reverse bias. So what happens if you have something like, so please read all these things carefully. I will give homework problem for you to practice these calculations. So this is a p-type, that means majority carriers are holes, right? So if I apply positive, because that's positive, right? If I apply positive voltage, that means you can make more carriers to move this way. That means you are making your depletion region thinner, because you are these holes. We had depleted holes here, right? Depleted electrons here. By applying positive voltage, you can repel some holes into this one and electron into this one. That means this depletion region, this W becomes much smaller. Initial this W is due to the built-in potential, right? So now you are making that built-in potential thinner. So we call that a forward bias. So if you have, that is actually this is a forward bias. So here I am applying negative potential to p-type. That means you are even moving some holes even from the initial depleted region. That means you are making this width higher. So what happens if you do this one? What happens to the bending? In this case, bending becomes lower, right? Initially you had some bending. In this way, now bending becomes here. Here, your bending becomes much sharper. Actually, in this case, you can even make the bends, we call the flat band. By applying enough potential, or already bent bands can be even flattened, right? That's called the flat band potentials. So you can see here you can see this is initially you had this built-in potential, right? We know how to calculate that value is basically that you have 1 over kBt times whatever, then log Na, Nd over Ni square, right? That's the VBI is given by that one here. Right? This is now I apply negative bias, your depletion region becomes much larger, then your bending is increased by that applied voltage. Initially it was only VBI, now this V applied voltage plus built-in potential. This becomes wider, this becomes larger. That's how diodes we tune the properties, right? So you can calculate all these, how much that your depletion width are changed by that applied voltage. So you will do all this in homework problems. So that's pretty straightforward. This is the forward bias situation. Yeah. So now we need to really understand exactly how this one works. Again, the same thing, right? P and N type. So here, these are majority holes, right? Here, majority electrons. So that means these majority electrons, they can only diffuse, right? So you have one phenomena, majority electrons will diffuse to this side, same way this has majority holes, that holes will also diffuse to this side. But at the same time, if you have a minority carrier, what are the minority carriers for N-type material? Holes, right? So that will respond to the built-in potential. So in this case, where's the potential, the electric field? It's to the right, because you have so electric field is this direction, right? It's a negative. So electric field this way means your electrons, the electrons will move to the opposite of electric field, right? That we call the drift current. Please remember these two currents, very important. Drift means in response to electric field, right? The diffusion means with respect to your concentration, gradient. So you can see by at zero bias this is the situation. Now if you have a reverse bias, so that means you have a much higher barrier here, right? So that means you have your barrier becomes the initial V0 plus V. So here this becomes much smaller because V0 minus V, right? So reverse bias. Now you can see how this one becomes much. So if your V is much larger, these two can be even like that. So here's a nice picture, please follow this one. This is P-type, that means this majority holes, right? That will diffuse this way. Here majority electrons, they will diffuse this way, but any minority carriers in your P-type, that will move this direction against electric field, right? So that's what happens in solar cells, right? In solar cells, your minority carriers are the ones respond to your built-in potential. You need to have a built-in potential first, right? So then you can tune it with the external bias. Is that clear? Okay, so let's talk about what happens in solar cells. I talk about basic functions of these PN junctions, right? So one is the diode. So everybody, we talked about how the diode works, right? Basically, so if you have a diode, so if you look at, typically we define diode like this, right? Positive and negative. The positive side, you have this until you reach certain breakdown volt, we call the offset voltage. There's no current, and this one basically. So we derive this equation. This current is given as E exponential E V over APT minus 1 some I0. So in the reverse bias, there are no current, but if it is large enough, then you have something called avalanche breakdown, right? Then you get some large negative current. So that's basically, but that's not a real interesting device, right? But you can make this PN junction more interesting in terms of solar cells and light emitting diodes and photodetectors and things like that. In solar cell, what happens? Again, PN junction, right? Silicon solar cell, you have a P-type silicon and N-type silicon. So then what you have when you bring together? Depletion region, you have a built-in potential, right? Built-in potential means you have this bend band, right? That way for everybody. Now, solar cell, what we do? We shine light. So, when you shine light, what happens? Electrons will move from, so forget about any donors and acceptors. So, if you are, so just basically think about simple band-to-band conversion. You have valence band, conduction band. I have light coming here, right? Some H nu energy. If this energy is large enough to overcome this band gap, so then you will get electrons to conduction band. then you have holes in the valence band, right? So, but remember, once we do this one, already there's the electric field. Where did we get that electric field? Built-in potential, right? Because we had the PN junction. So that means you have electric field. So you get these electrons and holes, so they can easily respond to that electric field. So that means if you have electrons, so they will move opposite of the electric field. Holes will move in the direction of the electric field. Thus, then at the end they will come to the contacts and you can extract the electron in the circuit. So here this is what happens. So, but there are certain other things happen. So this is already bent PN junction, right? So now I shine light, I make electrons to go from here to here, then you have holes here. So this electron doesn't go from here to here, right? So if this energy is much higher, they can go to higher state. But they are not stable at this point, right? They will like to come to the lowest possible energy. So how can it come? It has to make some collisions, mostly with phonons, right? You have lattice. So they will make collisions. Then what happens when this happens? You produce heat, right? Actually these electrons, your material becomes hot because they are colliding with phonons, right? So then it comes here. So once it comes here, what happens? You have a built-in electric field this way. So that will drift this way, right? Electric field this way, electron will come this way. Remember, these are minority carriers, right? Because this is p-type. What we have here? Electron. Electron in a p-type material is a minority carrier. That's the goes to this end. Then, so that they will just come out of the material. That's why it's important. You have to have two metals here, right? In the solar cell, you have to attach. Typical silicon solar cell, what is your metal? You have seen these large solar panels, right? What do you see? What color do you see as the contacts? Silver, right? You have silver lines. So that's the metal. That's why there's a lot of effort to replace that silver with some cheaper metals. So silver is still expensive, right? We have one group at Concenter, they are trying to replace silver with copper. That's much cheaper, but still a lot of issues, so it's not easy to do. There's a company called Bird Thin Films, they are going to make, replace silver with copper. That's much cheaper. Right? So then they will come out of your circuit, right? So then if you think about holes, so the holes also, so if these holes, so they also like to come here, right? They also make some collisions and come here and go like that. So then also sometimes when this happens, so at this point you have electron and hole. So they try to recombine. Is that a good thing? No, right? If you recombine, you don't get enough electrons out. So you need to avoid this recombination. So that's why you have to make some, these holes, they have this binding energy, right value, so that they don't recombine. If it's a very low binding energy, they always like to recombine, right? If it's a high binding energy, then they cannot recombine. You need to get as many as electrons coming this way and as many as holes coming this way. Then you get a good solar cell, right? So here is basically, here also you can have some recombination. These are not good things, right? So eventually you need to get, so if you recombine, what happens? It emits light, right? Typically, by shining light, you make electron-hole pair. By recombining electron-hole, you emit light. That's luminescence, right? So these are typical solar cells. This, you can have silicon solar cells, then you can have some other solar cells like cadmium selenide, cadmium sulfide, kind of solar cells. Then also we have these 6 different materials. So, but they all work on this p-n junction. So you have to have p-n and n junction. Also, you need to have some material that can absorb light, right? So if you want to create this one, you need to have the right band gap, right? Otherwise, you don't absorb. So that's why if you look at your black body diagram, everyone remember the black body radiation? If you look at your energy versus your lambda or energy, typically you see some kind of black body radiation. So typically, most of the energy is in this range. They are actually in the visible range. So then, if you are, this is more like UV, this is more like ultra IR range, right? You need to catch as much as light in this region. That's the highest energy, right? That's why people are trying to utilize this one. You don't get much from UV or IR, mostly coming from the visible. So that means your band gap should be matching that region, right? So like something around 1 eV kind of thing. So if you go to like 4, 5 eV, that's mostly catching UV, right? If you go to like 0.1 eV, mostly catching from IR. But still you can get enough radiation. That's why sometimes people make something called the tandem solar cells. You can have several solar cells. One will catch radiation from this region, some will catch from this one, and some will like putting in tandem. That will have more efficiency. So this is what happens typically, right? So we have light coming, then you are making electron hole. So then electron will go to one end and hole will go to other end, and you get current coming out, right? So you should not let electron and hole to recombine. So then we have to do some other techniques to make this light not passing through, right? It has to come through from one side, right? So then you make some kind of reflective surface so that that light getting reflected back and forth, so that means you can utilize the entire radiation. So then there are some other kind of solar cells called these organic solar cells. So these are basically polymer, fullerene was C60 molecule. So if you can attach this some kind of a functional group, we make something called a PCBM. So that's a organic the polymer. Then you combine that with another conducting polymer called P3HT. These are conducting polymers. So polymers typically they are insulating, right? But now people can make something called the conducting polymer. They are highly electrically conducting. These solar cells work as excitons. Excitons means, remember, in the typical solar cells, when you make electron and hole, right? So electron and hole, we usually let them move to the two ends, right? But in organic solar cells, when you make the electron hole pair, their binding energies are so small. That means they don't separate. They stay like one unit. What do you call this one? Exciton, right? So excitons are neutral particle, but they are one electron and one hole. So that's more like a hydrogen atom, right? So this basically hydrogen atom kind of. So you can easily calculate the entire energy states solved in the model, right? Except you have to use some dielectric constant. So in this one you can see you have this metal contacts and also another highly doped this conducting polymer has the two electrodes. So here you can see the regions. When you mix these two, you have regions of this PCBM, then some regions of the green ones are P3HT. So when you shine light, you are making excitons, right? They don't separate like in regular silicon solar cells. So they move as that one unit, they move from one end to other, actually to the this interface. You can see this region and this region, right? If you make exciton, they move through here until you reach this interface. At the interface you have what do you have interface? Electric field. Because of that electric field, that excitons getting dissociated. Because these are together because of some, they are always attract to each other, right? You have some binding energy. But if you have a high electric field, it can dissociate this one. But that happens at the interface. So then one electron will go this way and one hole will go other way, you get the solar cell. So this is the called the organic solar cells. Unfortunately, a lot of work going on here. The efficiency is not very high compared to silicon solar cells. Is that clear? So please remember, these ones work in terms of excitons. So next, light-emptying diodes. What's light-emptying diodes? In this one, we are going to recombine electrons and holes, right? So again, you make a PN junction, you have this built-in potential, EV0. So in the solar cell, what did we do? We shine light on this one, right? But in the LED, what we do is we apply some positive bias into this one. You apply voltage. When you do the voltage, what happens? Positive, the forward bias means your barrier becomes smaller, right? So now you can see your carriers, because if I apply positive charges, these electrons will move to this side against the electric field, right? So the holes will move this way, then this electron and these holes will recombine and emit light. Is it clear? So that means depending on your band gap, you can make different colors. Only thing you have to do is make a PN junction, apply positive bias and see what kind of light coming out. So people have done all this for what until, I don't know, the last year, did anybody attend when the Nakamura, when he was here, he was the recipient of that Liancon award. He's the one who discovered blue LED. People had LEDs from all the colors, from red to or blue, not blue, green, red, green and all, orange, all these colors, but they didn't have blue LED, because eventually what you need is a white LED light, right? To get white you need to combine all the lights. So they couldn't do that until they made the blue LED. So the problem was the band gap. So if for blue LED you need to have large band gap, like 3 to 4 electron volt. That was very difficult. So they had to use something called gallium nitride. These are the perfect material for blue LED, but you cannot make this material with enough purity. Lot of these defects there. But Nakamura found a way to make, but still lot of defects, but low enough to emit blue LED, the blue light. So that's very large band gap. That's why you got coming out light with blue. So gallium nitride is the one. If you use like others like gallium arsenide, all these will give you like red LEDs and things like that. But gallium nitride is the one we had to wait until maybe 4 or 5 years.
So you said it needed impurities?
Yeah, impurity means you have to minimize impurities. If you have impurities, then they can recombine not this way. It can recombine with some defect states, right? So that's not good, right? So that means you have to minimize the impurity states. So, but he typically, I think he managed to get like 10 to the power maybe 15 defects per unit volume. So that is still pretty high compared to silicon. We can make almost like no impurities, right? So, but even this was good enough to give enough light out. So then photo detectors. Remember LED works in the forward bias, right? So LED, the photo detectors usually they work in reverse bias. So you have to apply, first you make the PN junction, you have built-in potential, then you apply, so this is at speed equals 0, right? So typically built-in potential. Then you have to apply negative bias. So that means your barrier becomes high, it becomes larger, right? So then if you think about these two, actually they work in these two regimes, right? So LED, they work in the forward bias. So in photodetectors, they work in the reverse bias, means your voltage is negative. So this is where, so we call it a photoconductive mode or photodiode for LED or even silicon, the solar cells, you make the forward bias. So I hope everybody remember how the solar cell works, right? So how the IV characteristics for solar cell. If you take typical solar cell, solar cell is basically what? It's a PN junction, right? So if you look at I versus V, so this is how your it's not a solar cell, we call the dark current. So you have certain voltage, so then you get this one, right? But if it works as a solar cell, so if you apply if you expose to light, you will get current even without any bias, right? That's the solar cell. You get large enough current even without any. So we call this is open circuit, short circuit current. So that means this is typically dark current characteristics. For solar cell, it is basically something like this. So we call this is the open circuit voltage. Open circuit means your current becomes 0, right? So if you have to have a good solar cell, you need to have large short circuit current and also very large open circuit current. So this we call the fill-in factor. So ideal solar cell should have, this is more like a rectangle, right? So typically if your solar cell is bad, typically it can be something like this. That's not good, right? VOC and IOC are pretty small. You need to have as large as possible this fill-in factor to make a more rectangular kind. What people are trying to do is do the solar cell, we get as large as ISC, short circuit current, and large as open circuit voltage. So you can see this is how the solar cell works. So this is dark current. So here you can see this much if you are exposed to certain power of your radiation. So if you increase that one, you get larger. Right? So this is the solar cell. But if you use this one for a photo detector, if you want to detect something, right, some light, you have to work in the negative bias field. This is, we call the photoconductive mode for the photodiode. Yeah, and that's pretty much what I want to talk about these devices. So I think I will start superconducting in the next class. So let me quickly get started, then we can. Is there any question here? So I will ask you to derive the equation, then you will understand. It's basically simple electromagnetic theory. you have region of charges, you can easily calculate electric field. So next chapter is about superconductors. So I can just say, when we talk about superconductors, it's completely different theory now we are going to talk about. So far we were talking about everything based on what? Electrons and holes, right? So in superconductivity, you cannot explain from simple just electrons and holes. Instead, so they find some kind of this composite particle called Cooper pair. So this electrons and two electrons, but they have opposite momentum, so but they will always held together. So, but they can easily move in your crystal, so by actually influencing your lattice. So these electrons, when they are moving, since you have these two electrons, right, but they have opposite momenta, so they will kind of perturb the lattice, because that has that's why we call this electron phonon interaction. So the first electron, so moving forward, so that will perturb the lattice. So then the second electron will see that perturbation because it's already perturbed, right? So that's more like a electron phonon interaction, right? So that's whole thing is based on that, the electron phonon interaction coming from this, what we call the Cooper pair. So then all these Cooper pair, they are more like a bosons, right? So that means it doesn't have to obey the Pauli exclusion principle. So these Cooper pairs can be condensed into one ground state. Electrons you cannot, right? You can only have two electrons in a given state, but Cooper pair can do. Same thing if you talk about the superfluidity, we have these composite particles, so we have similar properties. So I will discuss about that one. The theory is completely different now. So it's not single electron or single hole. Two electrons together with opposite momenta. I will talk that one in the next class. Okay, too much. Okay. So after that we'll talk about the magnetism. That's the end of the class. Magnetism is a really big area.